Hello, Mr. Munyon here again with Activity 10-2, more on congruence. Alright, so in Activity 10-2, our focus is to determine whether figures are congruent, and we're definitely going to be using some sequences of rigid motion to prove that we have some congruent figures here. The first example here says consider the 5 labeled triangles. Just looking at these, which ones look like they're congruent, and why would we know that they're congruent? So A and B look like maybe that's just a rotation 180 degrees. C, maybe rotation 90 degrees from A. D, all of these, A, B, C, and D look the same. E obviously is not, because if I translate, A is not going to map onto E. So all of A, B, C, and D have some combination, maybe one or more rigid transformations that will map A onto B, C, or D. There is not a sequences of rigid transformations that will map A onto E. If you did a dilation horizontally and stretched it out, yes, but that is not a rigid transformation. So looking at question 1, it says shade all the figures that appear to be congruent. And how could we check these? So it looks like this guy here, here, here. All of those look to be congruent to A based on the fact I could do a sequence of rigid transformations to map A on top. All right. To prove two figures are congruent, a specific combination of rigid transformations must be found that maps each point P of one of the figures to corresponding P prime of the other figure. Predict whether the two triangles shown are congruent. Explain your prediction. So here it looks as though these appear to be, because I see side of 3, 4, right triangle, the hypotenuse, conveniently would be 5. It's a Pythagorean triple. So this is also a 3, 4, 5. I'm pretty sure these are. How could we confirm? We can do a sequence of rigid transformations to see if they map. Next question says, is there a single translation, reflection, or rotation map to map one of the triangles onto the other? Now, the book here actually says no, because the common sense thing here might be that we were to like rotate this first and then translate. Might be an easy one. Or you could translate then rotate. You know, let's say you translated here and then rotated. Not quite perfect, but we could do that. But there actually is a way to possibly do this with only one transformation. You could actually do this with a rotation, one rotation. The center of rotation would actually be about negative 2.5, 2.5. Let me show you that here real quick. Where is that at? Here we go. If I was to take these two figures and rotate about the point, take this figure, let's rotate it about the point negative 2.5, 2.5. And let's rotate this clockwise 90 degrees. Oops. I do see that, in fact, this does get A prime, B prime, and C prime all mapped on top of the other one perfectly. They literally translate or rotate exactly on top of that one. So our initial thoughts then would have been no, but there is actually a rotation. Yeah, I could have rotated the blue figure up there, the top figure, the Q1 figure, rotated So yeah, there is actually a rotation that we could do for that one. How could we do a rotation followed by a translation to map one figure onto the other one? We already mentioned that. There's a couple of different ways. Let's say we took this and we rotated about the origin. Let's say negative 90 degrees clockwise. We'd end up right here. And then if you translated to the left 5 units, so 1, 2, 3, 4, 5, that'd be an easy one to do. So let's go ahead and say that's what we did. we could first rotate about the origin, negative 90 degrees. And once we do that, we could translate left 5 units. So it doesn't go up or down, but it does go left 5 units. All right. Okay. Propose a composition of rotation and translation to map the triangle in the first quadrant onto the triangle in the third quadrant. We've done that. Then complete the table set for our proposal. So our rotation first would be about the origin, negative 90 degrees. And let's see where each one of these points end up. So the point that was at 0, 2 right here is now at 2, 0. What was at 0, 5 is now at 5, 0. So let's get both of those. And the point that was at 4, 2. So the is going to be pointing down is now at 2, negative 4. All right, I guess these are our coordinates, so I'll put the parentheses around there. The translation we did was to the left 5 units, so 0 minus 5. All right. You actually could have done this a couple of other ways. You could have rotated about any point and then done a different translation, but it should obviously have ended up back here. So if you tried this on your own beforehand and got different answers, there is more than one way to do it. Was our prediction correct? Yes, because rotations and translations is generally what we're going to use to map figures on top of each other for proving congruence. All right. Here, it says use this figure for 8 through 10. So it says predict whether the quadrilaterals are congruent. Look congruent to me. Yep. Good prediction. How could we test? Obviously, we could use a sequence of rigid transformations to map one onto the other. So follow our plan and test our prediction, identify the rigid motions that we applied. All right, so how could we get this one on top of this one? We don't just want to make it map. We specifically want to make it map on so A, B, C, D is congruent to B, E, F, G. So A is going to correspond to B. A on this figure is going to correspond to B on the right figure. And B on this figure is going to correspond to E. So B needs to be up at the top. So that being said, I think it's clear that I need to rotate it to positive 90 degrees here so that B ends up on the top. So the very first thing I could do is rotate it the positive direction, 90 degrees. And then from there, I need to move it exactly this distance here. So B ends up on top of E. B prime, I guess now it is, ends up on top of E. So I can do a translation along the directed line segment from B to E. So right there would map it on top. So going back to make sure we did these two things correctly, we need to rotate about point B so it's not going to move. So notice here, rotate about point B, positive 90 degrees. That's the first thing we did. Okay. After we did the rotation, we do a translation along the directed line segment from B to E. And we get them to map on top of each other. Okay, so far so good. Now we have question 11. Let me get this out of the way here a little bit. Says an arrow is placed. This is check your understanding. So pause here, try these on your own, see what you can do, and then unpause it when you're ready to check your answers. Hopefully you've tried them by now and we can check our answers. An arrow is placed with its base. So we've got it 0, 2. Oh wait, at the base is at the origin and the tip is at 0, 2. So we have the tip up there at 0, 2. For each arrow listed below, find the rigid transformation, composition of rigid transformations that shows the two arrows are congruent. So what if we had an arrow that had a base at 3, 3 and a tip at 3, 5. So base at 3, 3 and a tip at 3, 5. All right, looks like I just need a translation to the right 3 and up 3 would do that one. So if I took this to the right 3 and then up 3, that would map it exactly where I wanted to. All right, so translation. All right, so that first one, pretty easy. What if we wanted to have the base at -2, 2. So base at -2, 2. And the tip at -2, 0. Okay, there's a couple of different ways we could do this one. There's actually, you could rotate about the point -1, 180 degrees, and that would make everything flip around this point. I guess it's supposed to be clear. It's supposed to be pointing down. We could rotate about this point, and this is going to swing here. Well, that's not true. I guess the bottom is going to swing over here. The top is going to swing down there. But if you didn't want to do the rotation, because typically those, or if you wanted to use more than one, it'd probably be easier. You could rotate about the point 0, 1. So get it upside down 180 degrees, and then translate over. You could translate and then rotate. You could translate here and then rotate about the point -2, 1 if you wanted to do that. You could reflect across the x-axis, so you could reflect across y equals 0. That's going to make it end up pointing down here, and then translate left 2, up 2. Lots of different ways you could do this one. Let's just put one of those. Let's say we translated left 2 units, and then we rotated 180 degrees about the point -2, +1. So the first thing we could do is a translation to the, let's use a different color here. All right, translation left 2. And once we have it translated left 2, then I could do a rotation about the point -2, 0, 180 degrees. So rotation about the point -2, 1, I guess is what it is. Yeah, -2, 1, in the center of that one, 180 degrees. So translation first, and then a rotation, this one. It makes it end up where we want it to. What about if we... Okay. Oh, I guess I do still need the parentheses on there. What if it was at 4, 0 and 6, 0? The tip was at 6, 0. So 1, 2, 3, 4, 0 and 6, 0. The tip was there. We could probably do a rotation about the origin -90 degrees, so we get it pointed this way, and then translate over would be the easiest way to do that. So for this one, we could do a rotation about the origin -90 degrees. Whoops, I don't know why I put that on there. And then after we do the rotation, and it's right here, then translate over 1, 2, 3, 4 units. So translate right 4, doesn't need to go. So that would be another sequence that gets us there. For number 12, it says consider the right triangles shown below. Identify a composition of reflections that shows these two are congruent. So a composition of reflections. Okay, this one seems pretty easy. Looks like I could reflect this triangle here across AC. That way A would stay there, C would stay there, and B gets reflected across here. Once I have this one, I have A prime, B prime, C prime. I could then just reflect it across the line DC. So A would end up over here and map on top. So that one's pretty easy. First thing, reflect triangle ABC over the segment AC. And then over DC. So reflect there first to get the purple one. Once you have the purple triangle, then we reflect across DC. It ends up over there to map on top. Okay. For the next question, it says identify a rotation that shows these triangles are congruent. Well, obviously the center of rotation is C because that point doesn't move, and I could rotate it 90 degrees here is what it looks like, 45 and then 45 more. So it's going in the negative direction if that's clockwise. So rotate triangle ABC, negative 90 degrees, about point C. All right, so looks like so far so good. Rigid transformations, not too hard if we know the notation of how to do these transformations. Let's look at this section here. Actually, we're going to skip down to, we're not going to do this section here. This is basically says, hey, are these congruent? No, because there's not a set of rigid motion transformations. This is common sense. We don't need to prove that these aren't congruent here, so we're going to skip this section. A couple of check your understanding questions. Explain why a circle of radius 1 is not congruent to a circle of radius 2. Most people would say common sense, but based on what we've been using in this section, how can we prove things are congruent? There has to be a sequence of rigid transformations. And you can't get a radius of length 1 using rigid transformations to a radius of length 2 because you'd have to do a dilation. So there is no sequence of rigid transformations. Okay. Skip down now to 22 is where we're going to finish this one for today. It says the endpoints of AB are at -2, -1. So we have A at -2, -1. And B is at 1, 3. So I've already got B drawn here. Suppose you know that CD and AB are congruent. So I know they're congruent to each other. If the coordinates of C are at 1, 0, so this is point C right here, what are possible coordinates of point D? Okay, if they're congruent, they have to be same length, which means if I found the distance here, I could use a little bit of Pythagorean theorem. Looks like changing x is 3, changing y is 4. Oh, that's convenient. This is a Pythagorean triple. So we end up getting that this is a 3, 4, 5 triangle. So AB equals 5. And if they're congruent, that means CD also has to equal 5. And I can draw any 3, 4, 5 triangles to, there's literally, if you draw a circle here, there's an infinite number of points that are 5 units away. 1, 2, 3, 4, 5. Hey, there's one. 1, 2, 3, 4, 5. There's one. 1, 2, 3, 4, 5. There's one. 1, 2, 3, 4, 5. There's one. And any of these other points, some of them happen to be on nice grid lines, like 3, 4, or 3, 4. There's some more points because that's a 3, 4, 5 triangle. All of these points, and very quickly you start to realize like there's actually 1, 2, 3, 1, 2, 3, 4. You actually start creating a circle because any point on this circle is going to be 5 units away. Whoops, that last part looked kind of ugly there. So 1, 2, 3, 1, 2, 3, 4. 1, 2, 3. Whoops. 1, 2, 3, 4. 1, 2, 3. Yep, should be right there. Literally any of those points would be can make segment CD congruent to AB. All right, we are done with 10-2. Make sure that you try the activity practice from the homework schedule. There's also an embedded assessment video you should check out. It has practice with both 9 and 10. Some good practice there. So I will see you guys for the embedded assessment once you get there.